ES3C2 Group 23 Design Journey. Introduction. Group 23 designed a full double wishbone suspension for the rear left corner of a racing car built around a vehicle mass of 235 kilograms and a worst-case combined load as shown. The main goal throughout was to minimize assembly mass where possible. This video provides a walkthrough of our design. The wheel. It was decided that the rim should be comprised of two pieces, allowing for the face to be cast and barrel to be forged, followed by rectification, drilling, and tapping. The face and barrel components of the rim are fixed using a series of screws. Aluminium alloy A356T6 was chosen for the face, and aluminium 6061T6 for the barrel, owing to greater suitability for their respective methods of manufacture. Braking system. The torque requirements of the system was calculated to be 524 Nm. The final setup selected features the dual-cylinder caliper CP4227, carbon Lorraine sintered brake pads, and a 220 mm diameter disc to provide 758 Nm braking torque. A two-piece slotted and drilled design with bobbins to manage thermal expansion was selected via Pew matrix. Martinistic stainless steel AISI 416 was chosen for the friction ring due to manufacturer guidance and hardness, and aluminium 7068 T6511 for the carrier, prioritizing density. Shaft and hub. The shaft is a CNC turn-step cylinder featuring a 65 mm bearing bore stepping up to a 72 mm shoulder and a 3 mm fillet, giving a stress concentration factor of 1.82. Star pattern flanges and a central lightweighting bore bring the total mass to 1.84 kilograms. Under worst-case loading, the equivalent stress is 185 megapascals against an allowable 231.8 megapascals, giving roughly 20% headroom. So the part passes the infinite life fatigue check. TI6AL4V was chosen over steel and aluminium as it offers an 897 megapascal ultimate tensile strength and is 44% lighter than steel. Unlike aluminium, it has a true endurance limit, meaning infinite fatigue life can be claimed. Bearings. Tapered roller bearings handle axial and radial loads well due to their angled contact surface. Hence, two were arranged back-to-back to resist axial loads in both directions and maximize apex distance. 12 bearings were shortlisted by bore, outer diameter, and width constraints. 9 went through automated MATLAB testing and all passed. SKF 32913 was selected, being the lightest option at 0.32 kilograms, with an L10 of 404 million revolutions, providing an expected 650,000 kilometers use. Tapered roller bearings have no integrated seals, so two lip seals are fitted to both ends of the upright bore, protecting against contaminants. Wishbones and upright development. Wishbone calculations were executed to ensure the maximum force through the member stayed below 20 kilonewtons. An iterative process was carried out to obtain pickup point coordinates until a final setup was obtained and the upright finalized. The wishbones are joined to a weld cup, protecting the swivel joints from warping and crack propagation during welding. M6 flanged hex bolts and lock nuts were used for easy assembly and fastening to the upright. Annealed titanium alloy was selected for the upright and AISI 4130 steel, air melted, quenched and tempered, for the wishbones and weld cups, following a material selection process in EduPack to ensure the design could handle all forces which may be experienced, prioritizing low-density materials where possible. CVJ adapter. This adapter facilitates torque transfer between the shaft and CV joint. To manage reverse loading, 8 8mm spring steel dowel pins were utilized, achieving a safety factor of 8. The dowel pin assembly employs a H7/M6 fit with Loctite 648 to eliminate backlash, while a 10 micron axial interface ensures solid contact and pure shear loading. To reduce weight, perimeter cutouts were integrated, as shown by these cross sections. A titanium alloy was selected via Ashby analysis, prioritizing critical fatigue limits and surface hardness over lighter materials to ensure a robust, high-performance part weighing 0.7 kilograms. Final design. Overall, an assembly structure as shown in the animation was chosen for its simplicity, low cost, and ease of maintenance. Moreover, it does not largely inhibit air supply to the brake disc, aiding with thermal management compared to other setups. The final assembly has a total unsprung mass of just over 18 kilograms, with the three dominant unsprung mass contributors being the wheel assembly, shaft, and brake assembly.